Hello all, this is Maleeha Assistant Professor, Department of Electronics and Communication Engineering, Rajagiri School of Engineering and Technology, Kochi, Kerala. In this lecture, we shall go through an important circuit theorem, Superposition Theorem. If two or more independent sources are present in a circuit, we may apply mesh or nodal analysis to analyze the circuit. Alternatively, we may use the superposition theorem in conjunction with these analyses to derive the solutions. We shall look into the details of superposition theorem. We shall state the theorem and then see how it can be applied to both DC and AC circuits. The theorem states that the voltage across or current through an element in a linear circuit is the algebraic sum of the voltages across or currents through that element due to each independent source acting alone. This theorem can be applied only if two conditions hold good in the circuit: linearity and homogeneity. Linearity implies that all the elements in the circuit must be linear. That is, the voltage-current relationship in these elements must be linear. By homogeneity, we mean that if the input is scaled by a certain factor, the output must also scale by the same factor. Let us now take a look at the steps used while analyzing a circuit using superposition theorem. We consider the effect of one independent source at a time. Hence, we deactivate all independent sources except one. We do this by replacing independent voltage sources with short circuits and independent current sources with open circuits. We retain the dependent sources because they are controlled by circuit variables. Following this, we analyze the circuit using mesh or nodal analysis to determine the parameter of interest. We repeat the same step for all independent sources, one at a time. Finally, we add up the values of the parameter obtained by analyzing the circuit for each independent source and determine the overall parameter value. We shall now apply this theorem to a simple DC circuit. In the given circuit, we have to determine the voltage across the 4 ohm resistor, and we have two independent sources, a voltage source and a current source. In order to apply superposition theorem, we first consider the effect of the 6-volt source alone. To turn off the 3 ampere current source, we open circuit the terminals across which it is connected. Now we have a simplified circuit. The voltage across the 4 ohm resistor due to the 6-volt source V1 can be easily determined using voltage division rule as V1 is equal to 6 into 4 by 4 plus 8 volts, which is equal to 2 volts. Next, we consider the effect of the 3 ampere source. For this, we turn off the 6-volt source by shorting the terminals across which it is connected. Now, we can very well apply current division rule to determine I3, the current through the 4 ohm resistor. I3 is equal to 3 into 8 by 8 plus 4 amperes, which is equal to 2 amperes. The voltage across the resistor V2 can be determined using Ohm's law as V2 is equal to I3 into R, which is equal to 2 into 4 volts or 8 volts. The voltage across the resistor V in the original circuit can now be determined as the sum of V1 and V2, that is, V1 is equal to 2 plus 8 volts or 10 volts. Over other circuit theorems, superposition theorem holds special significance in AC circuits. This is because phasor analysis normally can be applied to a circuit only if independent sources operate at the same frequency. However, with superposition theorem, it is possible to analyze an AC circuit with excitations of different frequencies using phasor representation. We redraw the phasor circuit separately for each frequency and analyze it. Finally, we sum up the time domain responses to obtain the overall response. As an example, let us look at the given AC circuit. We have to obtain the voltage across the 1 ohm resistor. Here, we not only have 3 independent sources, but all the sources operate at different frequencies. Omega 1 being the frequency of a DC source is equal to 0, omega 2 is equal to 5 radians per second, and omega 3 is equal to 2 radians per second. Let us look at the phasor circuits at each frequency used in the analysis. For the 5 volt DC source, we short circuit the AC voltage source, open circuit the AC current source, open circuit the capacitor, and short circuit the inductor. The resultant circuit is shown. When we consider the 2 ampere current source with omega equal to 5 radians per second, we observe a phase shift of minus 90 degree since I of t is equal to 2 sine 5t amperes. We short circuit the 2 independent voltage sources, one AC and one DC. Now we replace the inductor value with its impedance at 5 radians per second given by the expression j omega L, and the capacitor value by 1 by j omega C or minus j by omega C. The resultant circuit is given. Similarly, for the 10 volt voltage source operating with an angular frequency of 2 radians per second, the phase is observed to be 0 degrees. The DC voltage source is replaced with a short circuit and AC current source with an open circuit. The impedances of the inductor and capacitor are computed at 2 radians per second. The phasor circuit is shown. Let us begin by considering the effect of the 5 volt DC source on the voltage across the 1 ohm resistor. After simplification, we can simply apply voltage division rule and determine V to be minus 1 volt. Note the reversal of polarity in the voltage V1 with respect to V0. Now consider the effect of the AC current source. The 1 ohm resistor is in series with the parallel combination of minus J2 ohm and 4 ohm impedances. This is in parallel with the J10 ohm impedance and the current source. We can apply current division rule to determine the current through the 1 ohm resistor I1. Applying Ohm's law, we determine the voltage V3 across 1 ohm due to the AC current source. Considering the effect of the AC voltage source now, we find that the parallel combination of the 4 ohm resistor and the capacitor is in series with the inductor and 1 ohm resistor. We can apply voltage division rule to obtain V2, the voltage across the 1 ohm resistor due to the AC voltage source. Having found the effect of the 3 independent sources on the voltage across the 1 ohm resistor, we algebraically add them in the time domain, that is, V is equal to V1 plus V2 plus V3. Summarizing the topic, we have seen that the superposition theorem provides a method of determining the voltage across or current through an element in a circuit having more than one independent source. Even though the method involves analyzing a larger number of circuits, that is, n circuits for n independent sources, all the circuits are greatly simplified compared to the original circuit.